This computer. Kristaps, you want to give us a title or just the same title, part two? Okay.
Part two, same title, part two.
Okay, ladies and gentlemen, welcome to another wonderful episode of the New York City Category Theory Seminar. Today we have Kristaps Balodis. He's going to talk about a geometric introduction to the local Langlands program. He spoke like 4 weeks ago and gave a wonderful, wonderful talk, and now he's going to go further with it, and we're welcoming him. We welcome him. Take it away.
Yeah, thanks. Thank you for having me back for part two. It's a pleasure. So thankfully, I still have all my notes here, so I'll just scroll through them quickly to give you a
We're,
refresher of the things we talked about a month ago. So geometric introduction to local Langlands program. We're talking about representation theory. We're trying to formalize things in a geometric way. And hopefully today I'll be able to start saying some somewhat more categorical statements that show up here. So um, generally, I'm interested in studying representations of p-adic groups. So things like matrix groups valued in the p-adic numbers, this GLN, SON, SP2N, all the classics, and then there's some other weirdos out there as well. And we're interested in studying representations plus some topological properties because these are topological groups after all. And I should actually correct, there's one error I made last time. I corrected this in the comments, but when I was talking about so the case of GL1 QP, so this is just the multiplicative group of the field. I said something a little bit wrong about the characters there. So the multiplicative group of p-adic numbers ends up factoring. Oh, I better, sorry, just quickly plug in my laptop here. Hold on, please.
we're doing the same thing here.
Similar issues abound.
So it factors as
Thank
it does factor, like I said, as the multiplicative group of the p-adic integers and p inverse. And so that gives us this thing over here, gives us something which is then isomorphic as a topological group to the integers times, so the integers is the powers of p inverse, zp cross, however, is actually isomorphic to the, I want to say p minus 1th roots of unity times times the additive group of the p-adic integers. And so understanding characters there is a result of understanding characters on each of these components. So I just wanted to correct that typo. Okay. So one of the ways in which we talked about, this method to try and produce representations of the groups that we're interested in is inducing them from smaller representations. So we were able to, given a representation of some subgroup H, we were able to create some space of functions on the larger group G, on which our group act by translation, and we called that an induced representation. In particular, for GLN, wow, I have some atrocious handwriting. For GLN, we looked at very special subgroups of GLN called Levy subgroups, which basically just look like products. They're look like products of smaller GLNs, where you just consider the subgroup of block diagonal matrices. And we talked about inducing representations from essentially these Levy subgroups, as we called them. There's some involvement of something called a parabolic as well. These are some technical details. And the big sort of pull for us is that in representation theory, we want to understand the irreducible representations. These are the atomic constituents, they're not built out of any smaller representations. And the big thing for us was the Langlands classification theorem, which more or less says, given any irreducible representation pi, I can find this special induced representation S pi, which I'll call the standard representation, that has a unique irreducible quotient, and that unique irreducible quotient is pi. So if I want to investigate all my irreducible representations, I can always produce them by inducing from some smaller subgroup. There are some exceptions. There are some where the induction is just the trivial induction, and so it doesn't actually come from uh, anything lower. Okay. So
One second.
one of the
Wait 1
things.
second. We're just getting the audio set.
Oh,
Hey,
Try
is everything?
The microphone on your laptop. Turn the microphone on.
one second. Okay, now try it.
Is everything good now?
Yeah, do you hear me?
Yeah, no more echo chamber.
Do you hear me?
Okay. I can hear.
Okay, go ahead, go. Sorry.
Okay. So one of the things that I had mentioned last time is that our category of representations, rep G, our category of representations, it breaks up into a direct sum of categories. It breaks up into a direct sum of categories. In particular, there's a very special component of this category we call the principal block. And what is the property? One way to describe the principal block, so I'll call it rep not of G. It's sort of this, in some sense, the most special summand in the category, but all of the summands are important. And what it was is it's a feature of this is that all representations, all the irreducible representations in this summand appear in the induction from the torus, a maximal torus of the group, where the representation is an unramified character. So to remind you what that means, say for GLN, the torus is the maximal torus is just the n by n diagonal matrices, and an unramified character of this group of matrices is one for which there exist complex numbers S1 through Sn, and the value of any one of these diagonal matrices is given. We simply take the p-adic absolute value of each one of these entries, put it to the power of the corresponding complex number, and multiply that result all together. And so everything in this, all the irreducibles in this category appear in something that looks like this. And one other special feature of this is, let's say we have a given, we fix some character chi, which is to say really just fixing a list of n complex numbers, S1 through Sn. Suppose I had two irreducible representations, or let me phrase it this way. Suppose I have an irreducible representation pi that shows up in this induced representation, and I have some other irreducible representation sigma belonging to this summand of the category. Then pi shows up in the standard representation of sigma if and only if sigma itself shows up in this thing induced from the torus. So it forms this sort of smaller family. It actually breaks up this big category into even smaller blocks that are labeled by these characters. So in other words, if I take two irreducible representations and I want to know, well, does pi show up in the standard representation of sigma? If pi and sigma don't embed in this same induction of a character, I know the answer is going to be 0. I can throw those out. And so I only have to answer this question. I just pick a character, I look at the induced representation, I look at the irreducibles in there, and I compare their standards just for this, what ends up being a finite family of representations. Okay. Any questions on that? That is a very quick overview of the representation theory we talked about last time. Great. So, how do we geometrize this, or how do we use this to state a geometric version of the Langlands program? So, we had talked about previously that each of these, every p-adic group has a sort of special dual group attached to it over the complex numbers, which we call g hat. The formal definition of how we construct this has to do with like Lie theory and root systems. But if you're willing to just black box that and accept the fact each of these matrix groups sort of has a special friend over the complex numbers. For GLN, it's its own special friend. The dual group of GLN QP is GLN-C. But for some of them, there's a swapping. So for SO2n plus 1 over the p-adics, its special friend becomes SP2n over the complex numbers, and dually SP2n over the p-adics, its special friend over the complex numbers would be SO2n. So they come in these dual pairs. Sometimes they're self-dual. And so we have these unramified characters. So I have this induced representation of some unramified character, by which I mean it's this character prescribed by a list of n distinct complex numbers. And I'm going to form, so I'm working over the some p-adic field, a fixed p. I'm going to form a element of GLN, which is given by taking the diagonal matrix, which is P, to each one of those complex numbers down the diagonal. And I form what's called a Vogan variety. It's really just a vector space, right? So the Vogan variety attached to lambda, this semi-simple element, is just all of the elements of my Lie algebra of GLN-C, which is just to say all n by n complex matrices, which has the property that if I conjugate by this diagonal matrix lambda, it has the effect of simply multiplying by p. In other words, it's the p eigenspace of conjugation by lambda. And this will be, so this is deceptive. I've written c to the n, but let me just move this out of the way here. I've written c to the n, but actually that should not be the same n as GLN. It will be c to the m for some other number. So I very quickly went over some examples from last time. So we could suppose that we had, maybe I'll rewrite these down below. So suppose, for GL2, I'm looking at the induced representation of GL2, which is given by the unramified character where the exponents are positive 1/2 and minus 1/2. Then my lambda will be p to the 1/2, p to the minus 1/2. And I can see what happens. I want to look at all matrices x, y, z, w, which when I conjugate by lambda, it has the effect of multiplying that matrix by 1/2. And if I'm doing the algebra correctly, this should work out to be x, py, p inverse z, and w. So the point is, this can only be true. Maybe over here, I'll multiply the p inside the matrix here. This would force, since p is a prime, it's non-zero. This forces all the entries to be 0 except for y. So in this case, v lambda is just all of the upper triangular matrices as y runs over the complex numbers. And we also have, I suppose I didn't introduce this last time, but there's, oh, I did actually. So there's also a group that acts on v lambda called h lambda. And that is instead, you look at the elements of GLN over the complex numbers, which are fixed under conjugation by lambda. So from this same computation, then, we can see that that would only be the diagonal elements. And since these are invertible matrices, in this case, we would get that h lambda is the group ST as S and T. So the diagonal matrices S and T is S and T range over all non-zero complex numbers. Why? What does this have to do with anything? What does this have to do with representations? So I'm going to give you the statement for this is, in a sense, a geometric version of the reciprocity map of the local Langlands correspondence. In the case of GLN, if there's time and interest, we'll talk about the extra sophistications that arise for other groups. GLN is deceptively simple. But the point is that the irreducible representations which appear in this induced representation from this character chi are in bijection with the orbits of v lambda under, oh, I suppose I didn't tell you what the action is. It's also conjugation. So an element G in H lambda acts on an element X of V lambda by conjugation. And so part one of the reciprocity is that there's a bijection between the orbits of this group acting on V lambda and the irreducible representations that show up in this induced character. I should say this, when I write this slash here, I strictly mean the collection of orbits. I do not mean to suggest that the quotient of this variety by this group is itself a variety. Again, that is definitely not the case in general. Yeah, so that's the basic idea. So in this case, for our particular example, where we've taken 1/2 and minus 1/2, we can see that the group acting, how does an element of H lambda act on an element of our variety? Well, once you conjugate, you end up getting that you multiply by S and divide by T. And so in this particular case, I claim that we would have two orbits. If y is 0, so I'll call C0 the first orbit. If y is 0, multiplying it by S over T will have no effect. It will simply remain the 0 matrix. That's a singleton orbit. If y were non-zero, then that means I'm allowed to divide by y. So I could take t to be equal to y. That would cancel out with the y, and I could choose s to be any non-zero complex number, which means if I had a non-zero y, I could send it to any other non-zero y. So the second orbit, C1, would be given by all of those upper triangular matrices where y is any non-zero complex number. So the prediction then of this geometric version of the local Langlands correspondence is that this induced representation of GL2 should have two irreducible representations in it, pi naught and pi 1. But the conjecture, as I've stated it at this moment, says nothing about how many times they each show up. So it could be pi 1, pi 0, pi 1, they both show up in there, but maybe one of them shows up 20 times and the other one shows up 47 times. So we really want to know, in order to actually understand this representation, yeah, I would really love to know how many, the full sort of list of composition factors, how many times did each of them show up? And then, of course, the more complicated issue of how do they glue together? And so here is where the business of the perverse sheaves get involved. So the Kazhdan-Lusztig hypothesis, so this is now something that you can put on top of the local Langlands correspondence. In fact, it sort of, the statement of it assumes you know the local Langlands correspondence, that there's this bijection between orbits and representations in here, is the following statement. So let me put it this way. Because it's a bijection, it makes sense to label, I'll put pi c, I'll use this label as the unique irreducible representation attached to the orbit C, right? And the p-adic Kazhdan-Lusztig hypothesis, perhaps version 1, is the following conjecture. It says that, suppose I have the standard representation of attached to the orbit C, and I want to know how many times the irreducible representation attached to the orbit D appears in there. Then the answer should be given by the sum over all integers of the nth cohomology group of the perverse sheaf attached to the orbit D. And one other thing I need to do is then ask how many times I need to restrict this down to the orbit C, and ask how many times the trivial sheaf appears in here. So I think I have some explaining to do of what all of these words mean. But very, very roughly, at a first pass, as to what the meaning of this is that these orbits that I've defined, in general, they will be singular. In this example I've written down, this is not the case. They're both smooth. And so the closure, for example, of C naught is just itself. It's just a single point. It's a closed point. I mean, this is Cn. It's just a manifold. And the closure of C1 is just going to be the entire variety itself, which is just a copy of the complex numbers. So that's smooth. And here's something that's not a coincidence. The closures of these orbits are, they're both smooth, and the multiplicity with which each of these representations show up in this induced character is 1. Let me give you one more example before I explain the right-hand side of this formula, the perverse sheaves. So let's just double up on our previous example, and let's consider an induced character of GL4. And now I'm going to take 1/2, minus 1/2, minus 1/2. And so my corresponding lambda is, of course, going to be the diagonal matrix P1/2, P1/2, P minus 1/2, P minus 1/2. And in this case, my V lambda, if we go through and do the same calculations, my V lambda now becomes the collection of all, these are block diagonal matrices. So this is all upper block diagonal. This is a 2x2 complex matrix. My H lambda becomes the group of invertible block diagonal matrices, where each of these blocks are invertible 2x2 matrices. And the action is given by conjugation. Which has the effect of just the A and B sort of conjugate this X. And the end result is that I end up having 3 orbits stratified by, well, again, we're going to have the zero matrix all by itself. But the orbits in this case are classified by the rank of the matrix. So Ci will be the orbit of upper triangular matrices such that that matrix in the upper corner has rank I. And there's 3 possibilities. It's either rank 0 when it's the zero matrix, it's rank 1 when it's the non-zero matrix but has determinant 0, and then it's rank 2 when it has determinant non-zero. So I have 3 orbits. And again, the closure of C0 is just itself. That's smooth. It's a point. The closure of C2 is, again, everything. So that is just a copy of C4. Now when I'm saying C, I mean the complex number C, C to the 4. Affine 4 space, if you will. But now it turns out that the closure of C1, this is just the union of the 2 orbits below. This has a singularity at the origin. So at C0, at the zero matrix. And it is not a coincidence that in this case, if we looked at our induced representation, and I ask how many times do each of my 3 irreducibles show up? Well, the ones, just like in the previous case, the ones that correspond to orbits with smooth closure, they show up exactly once. But in the middle case, it now shows up with higher multiplicity. And so the idea is that, so the local Langlands correspondence geometric version says that I have this bijection between orbits and irreducible constituents. But now, in addition, it says I can predict even more. I can predict how many times those irreducible representations show up, not just in this induced character, but in fact in between the larger set of questions of say the different standard representations, based entirely on the severity of the singularity of these orbits. And so that is what these gadgets on the right-hand side of the equation are meant to do. They are meant to detect the severity of singularities of these orbits. Okay, so now that we have some idea of the purpose of cohomology of perverse sheaves, now we'll say a little bit more about what they are. I'm not going to give... Oh,
one second. Yeah, so do you hear us? Can you hear me?
Yep.
Okay.
Yeah.
So like, I guess like a naive question is this like intersection multiplicity type thing? Is it really just like the multiplicity of the singularity in the naive sense, or do I really need this cohomology theory?
Uh,
Like,
it's not just the multiplicity in the naive sense.
like in other words, if I have a singularity, I can define the multiplicity of the
Right.
singularity by regarding it as a local ring and blah blah blah, right? It's
Right.
not that.
Right.
You're saying it's not
It's
that?
not it's not that. Yeah.
It's something
It
more
it
sophisticated. Okay.
yeah.
Okay.
But
So,
I'm actually not aware of how these things compare. I'm sure there's some relationship between these.
It's gotta be this.
Uh
I would bet it's like the same thing, right? I mean, how else would you get a number out of a singularity? I mean,
well, shoot.
the most natural thing to do would be to define the multiplicity of the singularity, right? I don't know. I mean, maybe I'm wrong, but it seems to me that
yeah.
that would be the most obvious way to get a number out of a singularity, like what you're talking about. But I don't know. I mean, this perverse sheaf business didn't show up for no reason. Yeah. So I mean,
Yeah.
like those are
I'm
some people. So yeah.
yeah, I'm not so sure. I mean, I suppose it's possible, but
It's okay.
I've certainly never come across anything that would suggest it.
But you were
And one
also
would,
saying, but you were saying
sorry?
things may not always be varieties, though. Because the multiplicity would be in the variety case, but you said there are quotients, they might be a rise, they might be stacks or something else, right?
Yeah, but you can still do this. I think you still have a way.
Yeah,
But you,
all of these orbits and these closures are honest to God varieties.
Oh, they are.
Uh,
Okay.
yeah. The quotient of V lambda by H lambda, that's not an
Yeah, that
honest.
wasn't right.
something else.
And
Like,
people do consider the stacky version of this. I tend to just think about, the varieties and whatnot, but
It's just a,
um
yeah.
yeah,
I would look it up,
I
man.
do think there's something more going on here than just that, but yeah, I guess I could be wrong, and I should probably look more into, what the precise relationship between those things is.
Oh, please tell me if you figure it out. I'll send you an
Okay.
email.
Yeah,
Okay.
I will actually, let me
but
make a note of myself.
it just that, because in the example you put, the thing that was singular was on the side with the orbits.
Yeah.
Sorry?
Well, in the example you gave, the singular
Yeah.
thing was on the side of the orbits, which is the side where they may not necessarily be varieties. Because you didn't even tell us what was on the other side,
Oh.
right? Because those are the orbits of V mod H, where you had the rank 2 and the rank 1 and the rank 0.
The orbits themselves will still be varieties, though. They're still defined by like a set of polynomial equations.
I think it's okay.
Okay, all right.
Yeah.
So
Okay.
another question from the amateurs. What do you go? Are we gonna look to resolve these singularities a la Hironaka or?
Yes, certainly. So certainly one of the methods of computation is that you take a good cover. So good in this case is a condition called semi-small. You take a good cover of your closure, and that's one of the ingredients that you need in order to do these perverse sheaf computations. Yeah.
Awesome, thank you.
I have a question.
Resolution.
Quick question. Can you hear me?
Yep.
Oh, okay, great. Yeah. So I was just wondering if you could make a couple of like analogies with sort of ordinary Lie theory, like complex semi-simple Lie algebras, let's say, like
Right.
just trying to, in order to follow, like V sub lambda, is that a weight space for a weight lambda? Is H lambda a Cartan subalgebra? And
Ah,
the irreducibles, is this orbit space going to somehow correspond to like a highest weight or something like that?
no, not quite. Not quite. Yeah, not quite. Although Yeah, the V lambdas are always going to be well, at least for this principal block case, the V lambdas will always be contained in the nil cone of the Lie group. I don't know if you're familiar with that terminology. The H lambda itself will always be a Levy subgroup. But yeah, it's the analogy isn't so direct that you should be thinking of the H lambda as like a cartan, or even the lambda as like some sort of weight. Um, well, uh, there is a way actually to discuss this language in terms of how the roots are acting, and in fact, you really need to take this perspective once you start talking about the exceptional Lie groups like E8 and stuff, just because you're not going to pick a matrix realization for these things because it's unmanageable.
Right.
But yeah, it's actually it's not so direct because remember at the end of the day, the representations we care about are for a p-adic group. And so it's not so direct that we're constructing these representations of the p-adic group out of this complex geometry. Um, if there's time and interest, I can say a little bit. I mean, I'm hoping I can make one sort of categorical statement about how one can get to representations of a p-adic group literally built from this complex geometry, but it's a little weird. It's not so direct as you might expect. Yeah.
Okay. Thanks.
Okay. So we have this bijection between irreducible representations and orbits, and we at least have this idea that the singularities of these orbits should be telling us something about the multiplicities of these representations. But the exact way that we talk about these singularities of orbits is the following. So we're going to consider on one of these orbits, in general, we want to consider what's called a local system. And in fact, we'll want to consider something called an H equivariant local system. It makes it slightly fancier, but I mean, well, if you don't want me to bury those details under the rug, I don't have to. But the main important thing here is just that it's a local system. So what is that? It's a locally constant sheaf. What is that? Roughly, it's a family of vector spaces that sort of varies smoothly across your orbit or whatever variety you're on. And you might think, hey, that sounds an awfully lot like what we just call a vector bundle. You're absolutely right. There is some connection with vector bundles here. For anyone who knows what this means, it happens to be the same as prescribing a vector bundle with a flat connection. So it's something more special than a vector bundle. But the easier way to just think about it for now, it's you just vary over the points of your orbit. You sort of smoothly vary some family of vector spaces.
So these are going to
So
be
the
vector spaces here. They're
sorry.
going to be so they're going to be sheaves of vector spaces.
Sorry, can you say that one more time? It just wasn't
The
clear.
sheaves you are talking about will be sheaves of vector spaces.
Oh, yes, yes. In fact, a sheaf of complex vector spaces specifically.
Okay.
Yes. Yeah. Yeah. And so I mean a classic example is what I'll call 1C. So this is the constant sheaf on the orbit C. So it's a vector space as dimension 1 everywhere. Now I should say there's more than one sheaf, more than one local system that might have dimension 1 everywhere. There can be more sophisticated ways they glue together, but one thing we're always guaranteed to have is the constant sheaf. And we have a special kind of perverse sheaf called an intersection cohomology complex. that is associated to this pair, C and L, a local system on it. So at the most basic level, what is a perverse sheaf? It is an object in the constructible derived category of sheaves. So what I mean by that is it's a sequence of sheaves. I have some sheaves. Maybe I should give it upper indexing. So it's some sequence of sheaves with maps between them. And there's some sort of fancy definition, the full general definition of perverse sheaf is some fancy thing, some fancy bounds about when it can't be zero and when it has to be zero. But the idea is that complex, this complex of sheaves, what it's measuring is the ability to extend L to a local system, to one of these locally constant sheaves on the closure of this orbit. So if we go back to this example where I had p1 half, p minus 1 half, I had two orbits. I had C naught, which was just the zero matrix, and I had C1, which is just the upper triangular matrices where y is non-zero. And both of these have smooth closure. And the effect of that is that there's no issue extending these local systems to a local system on the entire variety. And basically, the obstruction that could possibly exist is singularities. So the intersection cohomology complex of the constant sheaf on the trivial orbit on C naught is just the sequence that has the constant sheaf, or let me say it this way, because this should be a sheaf on the entire variety V lambda. So what it is the skyscraper sheaf. This is notation for the skyscraper sheaf on V lambda. So it's just it's the sheaf that's concentrated just at the origin somehow, and then everywhere else it's zero. It's that in degree zero, and then every other part of this complex has degree zero. And the fact that there's no trouble, the closure of C naught is itself. So of course there's no trouble extending this to C naught. And so we see that there's no other terms popping up precisely because there's no issue extending this local system to the closure. In the exact same way, for this, for IC, if we take the orbit C1, again, this is an orbit with smooth closure, and there's no issue extending this to the entire, to the closure of C1, which is the entire variety. So what we end up getting is the constant sheaf on the entire variety, except this time it lives in degree 1 actually -1, degree -1. And okay, there's something to the shifts, but again, we see it's entirely concentrated in 1 degree. And this is, again, a manifestation of the fact that there's no issue extending this to the entire variety. Compare this, however, with the IC. So if we go to the GL4 example, where we now had these 3 orbits which were stratified by rank, the intersection cohomology complex associated to the middle orbit, is this right? So I should have prepared the calculation ahead of time, but I believe that in this case, I don't remember the degrees, but the point is that there should be 2 locations there should be two locations where something comes up as being non-trivial. And this is sort of that manifestation of this two popping up. Now, there's maybe one more thing I need to say. So here I haven't talked about why are we taking the cohomology of the complex and not just looking at the complex. Well, I mentioned that this is a complex of sheaves, and we're ultimately working in the derived category. And so in the derived category, you could have different complexes representing the same cohomologies, right? So you could have a complex where maybe each of the individual terms in this complex are non-zero, but the cohomology of this complex everywhere is zero. And so I've really been lying a tiny little bit by saying, oh, all of these things are literally zero, and the thing in the middle is literally this sheaf. What it really is that say in this example, there's two values of the cohomology of this complex.
Well, you were just picking a particularly nice resolution.
Yeah.
Sorry?
You were picking a particularly nice resolution. The right
Yes.
thing to pick a resolution and pick a nice one that happens to have a lot of zeros in it.
Yeah. Well, this one, I mean, the way that this is actually defined, it doesn't sort of go through like the normal way of like, say when you're deriving a functor, right? You take your object, you approximate it by some nice resolution, you apply your functor, and you take cohomology. Well, okay, actually, I guess I suppose that is secretly what's happening. That is secretly what's happening. The actual definition has you taking this local system on C1 and applying some derived functors, which I guess technically has you uh, um, choosing resolutions in order how to define it, but applying some particular derived functors that push it into the derived category of the whole space. Yeah. Okay, how am I doing for time here?
You got it's 2:50.
So I suppose in the next 10 minutes I will try to say something more about some sort of way of connecting this category of perverse sheaves to this category of representations. I'll see how far I can get in 10 minutes, but I'm also happy to stick around for as long as people like to
More than
answer.
10 minutes.
Sorry?
More than just 10 minutes. We can.
Oh, more than just 10? Okay, great. Then I mean, just let me know when you're tired of hearing me speak, I suppose. Good time for a sip of water, though, in between. So, part of what I'm about to say, so we have this Kazhdan-Lusztig hypothesis. But why should it be true? And how do we prove that it's true? It seems like we're very loosely connecting some very disparate objects, right? Like potentially infinite dimensional representations of some p-adic group combined with like local systems on some loosely related semi-simple group. It's a very strange sort of thing. And so I'm going to highlight the sort of original bridge that was laid out by Chris and Ginsberg. There are other approaches to this now due to people like Lustig and Soleveld, which have established it in more generality. But I've sort of spent most of my time thus far, thinking about the original approach. So, the way that we connect these things is, and I should say, both the approaches are sort of thematically similar. So the way that we're going to connect these things, so we have this important block, right? This principal block of our category. And it turns out that this is equivalent to a module category over a particular kind of algebra called an affine Hecke algebra.
One thing, before, you probably said it again, but what is rep zero? I've probably forgotten.
So rep zero, it's the principal block of the category of representations of G. So what that means is our category of representations, it has this nice direct sum decomposition. And one possible way to explain what the principal block is it's the full subcategory generated by those irreducible representations that show up in one of these induced representations from the torus. So one of these unramified characters being induced to the torus. This is one possible way to describe it. And well, I mean, in general, representation theory of finite groups, that's equivalent to some module category. And so, it makes sense that we get these sort of approximate results for representations of more fancy groups, where now the affine Hecke algebra, I should say, maybe it is an affine Hecke algebra, but it's also sometimes a very particular instance of this is called the Iwahori Hecke algebra. So what this is again, if you were mimicking the case of what happens for finite groups, you would probably try to think about something like complex functions, complex valued functions on your group. Again, this is a topological thing, so now we want to take, maybe something like continuity. If you recall from last time, the special words for us was locally constant. So that was the sort of special topological word we used. And it turns out you can do, it's actually the case that the entire category of representations, forgetting about the blocks, but the entire category of representations is equivalent to modules over the locally constant, compactly supported functions on your group. But in some sense, this is a terrible ring to work with. It doesn't have unity, so some people wouldn't even call it a ring. And in any case, we're sort of interested in this smaller block, and it turns out that you can carve out this smaller ring that just sees this principal block. And so what it is we have to add that these functions are bi-invariant under some special compact subgroup called the Iwahori subgroup. Hence the term Iwahori and the introduction of this I. This I is this nice compact subgroup. Okay, so we go from representations over to this module category. And this happens to be right, one of these affine Hecke algebras. In particular, I'm not sure if anyone's familiar with like Schur's lemma. What's it called? Schur's lemma in representation theory. Basically, it says that each of the irreducible, if you have an irreducible module for this algebra, then the center of this algebra should just act by a scalar.
Mm-hmm.
So it should be some, I guess you could call it a character. So each irreducible representation will act by some character. And if you look at the ideal generated by the kernel of this character, and you take the quotient of your ring, basically the point is that the irreducibles, the irreducible representation, so let me introduce some notation. I'll call this H sub chi for short. The irreducible representations of the full algebra with central character chi will be exactly the irreducible representations of this subalgebra.
Mhm.
And here is now something perhaps entirely crazy. Maybe you think all of this is entirely crazy. But what Chris and Ginsberg do, so we have these Vogan varieties, and it might seem weird to come up with some cover of them because they're already smooth, they're already affine space. But what they do is they come up with a special cover of these varieties. They we'll call this map mu. They push forward the constant sheaf on this cover, and they look at the extensions of this perverse sheaf, or sorry, of this. Well, technically, after we shifted, it is perverse. But of this push forward, this sheaf that's been pushed forward, and I'm gonna call this, since this depends on our lambda, I'm gonna call this E lambda. And remember that lambda depended on some. Okay, yeah, I'm gonna call it E lambda. And so here's the sort of maybe shocking, strange thing that they do in order to prove the Kazhdan-Lusztig hypothesis. They say, okay, start with we're investigating the principal block. We know that every irreducible module, every irreducible module for this algebra admits a central character. We'll fix a central character. Well, I should say, sorry. I apologize. I got myself a little turned around here. Let me start the story here. So we're fixing some chi, which is a character of the torus. And we're looking at all of those representations appearing in this induced character. That induced character, it turns out, this chi determines an omega, just to give it different notation, it determines a central character of this Iwahori Hecke algebra. And in fact, there's a bijection between such things. So the irreducible representations that show up in this induced character will be exactly, once you pass to this equivalence of modules, will be exactly the irreducible modules that have this omega chi. So they'll share the same central character of this module. So
H,
H,
H now is homology or Hecke?
sorry, this H is Hecke.
Okay.
This H is Hecke. Yeah, perhaps I probably should have called it a different H. It's a little late now, but yeah. So now you look at that algebra, which is the quotient by this character omega chi, and the sort of stunning result is that this is isomorphic to E lambda, and I'm going to call it lambda sub chi. So remember in this whole construction, we started by taking some chi, and that told us how to define lambda, right? So like here in this example, this was our chi, and that told us how to define lambda. And so this is sort of the gateway between these two worlds is, and this is sort of the big result of Chris and Ginsberg, if you will, that allows one to pass between these worlds and relate the cohomology of perverse sheaves to these multiplicities of these representations, which is this statement that this algebra here, which is built out of complex valued functions on your p-adic group, is isomorphic to this strange extension algebra between some sheaves on your Vogan variety of Langlands parameters. So this is the way that you actually build the passage between these two worlds. So that's a lot.
Yeah, yeah.
uh, uh,
Kristaps,
yeah.
if I'm sorry, I just want to go back to like what's surprising about this result, and
Ah,
it and if you can, if I would like, rather than me trying to guess it, I'd love for you to like say what what the leap is and how, like, what's surprising about like connecting the p-adic numbers and the multiplicity of this, because I want to like try and keep the motivation at the top of my thinking.
sure, sure, yeah. So now I should say let me qualify. I found it surprising. I'll talk about why I found it surprising. I mean, maybe the people who proved this didn't. You know, maybe on some level they're like, oh yes, of course these things should be related. But I'm certainly, after many years of thinking about it, I'm certainly still surprised about these things. So um, I mean, just a priori, right? On the one hand, if we start at the very beginning of this with the concept of the irreducible representations of GLN QP, I don't know if you recall from the first talk, but I mentioned that there's some characters of GLN, and those are all the interesting finite dimensional representations, actually. All the irreducible finite dimensional representations are one dimensional. And then, boom, all of the other interesting ones are infinite dimensional. So, like, part one of one half of the story is generally about infinite dimensional representations of some p-adic group. The topology on the p-adic numbers is very different from the complex numbers. They're worlds apart from each other in some sense. And we're dealing with, infinite dimensional things. There's harmonic analysis going on. There's a lot more analysis going on than I've even let on. There's all sorts of, you're doing crazy integrals and whatnot on these function spaces. And from my mind, at that very sort of basic first glance, this is quite far away from uh, complex varieties and, the cohomology or singularity of complex varieties. I mean, if you had asked me 5 years ago before I began my PhD, hey, Kristaps, do you think those two things are related? I would probably say no. But I guess, I don't know. The math is also full of interesting connections. So maybe I shouldn't be surprised about any of this anymore. So that's why I find it surprising. There's another reason you could argue this both ways, and that it might give you hope there's a connection, or it might make you less surprised. And this actually has to do with what someone asked earlier about the highest weight spaces and whatnot. So the original version of the Kazhdan-Lusztig hypothesis, so not the p-adic version, but sort of like the original one for complex groups, you're studying basically representations of a Lie algebra G. And you say, okay, well, actually, studying representations of the Lie algebra, that's basically the same as studying modules. So maybe I should write rep G. That's maybe slightly more appropriate, because G, of course, isn't actually an algebra. But what you can do is, you can pass to its universal enveloping algebra, and that is an honest to God algebra. You can consider those representations as modules over that algebra. And well, if for those who might know a bit of Lie theory, the Lie algebra, right? We interpret this as a tangent space, and the universal enveloping algebra can be thought of as a collection of differential operators. So Now, modulo, understanding what a D module actually is, other than vaguely, it's a sheaf of differential operators. So it's a module over the sheaf of differential operators. So it's some sort of geometric gadget that has an action of differential operators. Well, you just heard the word differential operators, so maybe it's not so incredibly crazy to think that this should have something to do with D modules on. So I should say G is a complex Lie group. Little g is its Lie algebra, and B is what we would call the Borel subgroup of G. So G mod B is like some flag variety. So the classical Kazhdan-Lusztig hypothesis goes like this. It says, I want to study representations of my Lie algebra, but actually those are modules over my universal enveloping algebra. But actually, those are just things that, have some sort of action of differential operators, which we essentially call a D module. And then finally, the famous Riemann-Hilbert correspondence says, well, actually, D modules are the same thing as perverse sheaves. Now, I don't want to undersell how difficult and important it was to prove all of this, but at least in my mind, the story is quite clear about how you start with a representation of a complex Lie algebra and you turn it into some other form of complex geometry. And I hope that at least I've conveyed some, modulo not understanding some of the technical definitions of these terms. I hope I've conveyed some plausibility just, based on the similarity of these things. Meanwhile, the question is, how do we approach this for p-adic groups? Because for p-adic groups, I mean, it's this part of the bridge that now becomes difficult because here, I mean, this is, you would think that maybe you end up getting some sort of notion of D modules on some sort of variety over the p-adic numbers, maybe. But as far as I know, there isn't really a good notion of that. So for to me, it's much more surprising that this sort of gap here can be bridged, right? I would expect somehow p-adic things to be related to p-adic varieties. And yet
Right,
it turns out, sorry?
and it's not even clear how you would define a D module over a p-adic group, given
Yeah,
that everything is a twist or a cusp or like there,
yeah,
there's nothing smooth. It's not singular. I mean, it
yeah,
is singular.
yeah.
It's not regular.
Yeah, and look, I mean, there is some notion of p-adic differential equations, by the way. So you might think, oh, maybe there's some way to talk about some sort of p-adic notion of smoothness, but it's the p-adic. It's weird. You can't like the same things just don't work out. The same things just don't work out. So yeah, it's not at all clear. And so to me, you know, I find this isomorphism, quite mysterious. And actually, speaking of quite mysterious, I mean, uh, part of what I needed to do for my thesis, well, I found a different way around this, but the original game plan was try and understand this isomorphism very explicitly in terms of what it's doing in terms of generators and relations, because this algebra on the left-hand side, we actually have a very good understanding of its generators and relations. This theory has sort of been worked out. But this thing on the right-hand side, I mean, to me, it's built out of these very fancy geometric objects, and I just don't know how to interpret it. And I mean, Chris and Ginsberg, they have this book. They write down the proof. You can follow the proof, but there's the proof of it ends up passing through like 20 different isomorphisms, and it's just not at all clear on a very like explicit like let's do a computation level as to where each of the well understood generators on the left hand side, how to interpret those as geometric things on the right hand side. So, to yeah, to me, this is a very surprising thing. Yeah. Um, so I suppose maybe since I've already started sort of going off on a tangent on questions, maybe this is a good place to stop the official talk and switch over to questions.
Sounds
There
good.
We
is,
got some categorical things, and I
yeah.
remember earlier in the beginning that you said there were some categorical things you might want to mention.
Yeah. Yeah. So I mean, I guess there one of the things okay, I'll say a couple of the things. So well, I suppose this is one of the categorical. You could say it's not very deeply categorical. You know, it's just an equivalence of categories. But to me, this is a very magical equivalence of categories, which is mediated through this isomorphism of algebras, right? It takes us from a subcategory of the category of representations over to some module category built out of these perverse sheaves. Someone at the very beginning of the last talk asked me, I think, about Koszul duality. Because I think we were talking about, is this, is there equivalence of categories between the actual perverse sheaf category and the category of representations? And the answer is no, but there is a certain kind of derived equivalence going on called Koszul duality, and one of my academic siblings, or I guess we're both graduated now, so I should say ex sibling, step sibling, I don't know. He, his thesis was about this Koszul duality phenomenon in a very special case. So I should say that this isomorphism of these algebras here is sort of a hint or a shadow that these Koszul duality equivalences are happening. But at the moment, I mean, we don't know that this holds in general. Like there's sort of uncharted territory here in that regard. One other thing is the original way I explained what the p-adic Kazhdan-Lusztig hypothesis was about was this map of Grothendieck groups and some sort of pairing. So I gave you one version that directly relates these multiplicities in terms of multiplicities of irreducibles in a standard representation in terms of stocks, cohomology stocks of some perverse sheaf. There's an equivalent way of formulating it where now I can explain some of this a little bit better. So on one side, so we have our let me call it maybe rep chi G. So those will be all of the representations that that appear in our induced character chi. We look at the Grothendieck group, so sort of the free group on the irreducible representations, and we define a pairing between that and the Grothendieck group of the corresponding category of perverse sheaves. So remember, chi determines our lambda here. And one way to phrase the Kazhdan-Lusztig hypothesis is to say, so it's true if and only if these two pairings are true. Sorry, if both of these pairings are equivalent. So pairing number one says you take an irreducible representation pi. It's pairing with the, let me write it this way now that we have some more notation. So let's say pi c, the unique irreducible representation attached to the orbit C, and the intersection cohomology perverse sheaf attached to D. It will be 1 if and only if C and D are equal and 0 otherwise. So that's pairing number 1, is pairing the irreducibles with perverse sheaves. Pairing number 2 is pairing, I should say, the local systems. So this is part of the stuff of the more complicated story beyond the GLN that I was sweeping under the rug, is we have these non-trivial more local systems than just the constant sheaf now. And so there's a little bit more data to consider. But again, the idea is roughly you take the pairing that pairs the standard representation of the unique irreducible attached to C and the trivial the trivial sheaf from the orbit C. And again, you say that this is 1 or 0, depending if C or D is equal. And I guess technically, I need to push in order because this is happening on the growth and D group of on your full variety. You need to push this thing forward into the full variety. And one reason that I wanted to bring this up is that yes, we lose a lot of information by just going to the growth and D group, but there's very interesting relationships between different functors. So the induction functor, which is really important to us, seems to have this very special property. So I have some subgroup, right? I have some subgroup M of my group G. My induction functor takes me between the categories of representations. And conversely, if I have this, Vogan variety for V, or for my group G, I also have a similar Vogan variety for the group M, and I have an inclusion. It turns out that one variety embeds in the other. And with respect to this Kazhdan-Lusztig pairing, the induction actually turns into a linear transformation between the growth and D groups, and taking a pullback along this inclusion turns into a linear transformation of the growth and D groups of the derived categories. I should also add there's plenty of things like words like equivariant that I'm leaving out of here that are extremely important, but I want to get the concepts across and maybe not all of the technicalities. And it turns out that these linear interpreting these as linear operators on the growth and D groups actually defines an adjoint pairing, a pair of adjoint maps with respect to this pairing. And so there are these interesting manifestations, there are these interesting functors on either side of the Langlands program here. So functors relating categories of representations between groups, and other functors that are relating sheaf categories or derived categories between these varieties. And they somehow seem to be manifestations of each other. They're dual to each other in some sense. And so this is but one of the sort of interesting phenomenon that again, this is very sort of p-adic thing versus this complex geometry thing, and yet these somehow you can see these special relationships through this Kazhdan-Lusztig pairing.
Yeah. First of all, I think we should just thank you. It's a beautiful talk, and we should all thank you.
Thanks.
Are there any questions from online? Andre, thanks you too.
Oh,
We have a question here. Take it away.
oh yeah, well, it's online, but
No, you're online.
okay.
Nobody's online.
Yeah, we're all online.
You're on this line.
All online. Okay, so is this pairing, can this pairing be regarded as some type of intersection pairing?
I don't think so. I mean, it on one hand, it's eating, like, one component is eating representations of a p-adic group, and the other component is eating perverse sheaves. So
But what does it really do, like, down at the at the finer level, right? Like, I mean, sure, yeah, the very coarse level, it's doing that, but like, how do you actually get the number? You know what I mean?
Ah, I see.
Yeah, how do you get a number at the end? You have to get an integer, right? So how do you do that actually? If you don't know, it's okay, but like
Yeah.
ultimately, in my experience in math, every time I see a pairing, it's an intersection of some two things. I have never
Mm,
seen a pairing that cannot be regarded in that way. So I would wonder
mhm.
if this is like some type of intersection of two things.
Okay.
You know what I mean?
Yeah.
It's core, obviously not like
Um,
through course, but it's okay if you don't know, it's fine.
yeah, I don't there's certainly no obvious way to me to view it as an
That's okay.
intersection of things, but yeah.
Because like a lot of this perverse sheaf stuff and the intersection cohomology, right, is like very much about that type of stuff, yeah.
Right.
So,
Yeah.
and the people that made this stuff, right, like Goreski and McPherson, they were thinking very much about intersection theory in a very classical way, like super
Yeah.
classical intersection theory.
Yeah.
So I would bet that there's something like that kind of under the hood, but it's just
Mm,
not like apparent. So, okay, thanks.
yeah.
Okay, let's thank. Any other questions? Let's thank the speaker again.
Mm,
So this was excellent. Everyone else, we're going to meet next week. We're going to have another talk next week. You're all welcome to join. Thank you very much.
All the way into June.
Well, yeah, we're going all the way into June. We're barely missing any week. Okay, let's pause the recording.
yeah. Yeah, thanks again for having me.